Dear viewers, welcoming you all to the session on asymptotic notations. The agenda for the session is about one on complexity, asymptotic notations, big O notation, as well as big omega notation. Algorithm complexity is concerned about how fast or how slow an algorithm runs. Complexity is defined in a numerical form as T of n, that is, time taken versus the input size n. An algorithm with same input size n takes different amount of time on different systems based on factors such as processor speed, instruction set, disk speed, and the brand of compiler we use. For example, let's take addition of two numbers or two integers. The time taken for addition of two integers can be represented as T of n is equal to C into n, where C is the time taken to add two bits and n is the input size. Assuming C1 is the time taken on one system and C2 is the time taken on the second system. Thereby, T of n can be equal to C1 into n on system 1 and C2 into n on system 2. Therefore, different system results in different slopes, but T of n grows increasingly as input increases. Complexity is concerned about all these, such as how fast an algorithm runs or how slow an algorithm runs. And as discussed earlier in the previous slide, how the time taken has been represented as T of n, and n, which is actually the input size. And depending on the different input size, different time has been taken by different systems. So here, let's explore algorithm complexity on and the various factors that influence input, ultimately impacting the performance of algorithms. Understanding these factors is essential for analyzing and optimizing algorithms to achieve desired efficiency and scalability. Let's look into this in detail. The speed of the processor or central processing unit plays a significant role in algorithm performance. Modern processors vary in terms of clock speed, number of cores, and architecture, affecting the execution time of algorithms. Faster processors can execute instructions more quickly, leading to shorter runtimes for algorithms. However, it's essential to note that algorithm performance is not solely determined by process speed, as other factors also come into play. The speed of the disk, including hard disk drives and solid-state drives, influences the input-output operations of algorithms. Algorithms that involve reading or writing data from or to a disk may experience bottlenecks if disk speed is slow. Faster disk speeds result in quicker data access and manipulation, reducing the overall runtime of algorithms that rely on disk input-output operations. Optimizing disk access patterns and utilizing caching mechanisms can help mitigate the impact of disk speed on algorithm performance. The instruction set architecture of the processor affects the efficiency of algorithm execution. Different processors support varying sets of instructions, with some instructions executing more quickly or efficiently than others. Algorithms optimized for specific instruction sets may perform differently on processors with different architecture. Understanding the target problems, the instruction architecture, and optimizing algorithms accordingly can lead to significant performance improvements. The choice of compiler and its optimization settings can influence the performance of compiled code. Compilers translate high-level programming languages into machine code, optimizing instructions for execution on the target platform. Compiler optimizations such as loop unrolling, instruction scheduling, and memory layout optimization can impact the efficiency and speed of algorithm execution. Choosing an appropriate compiler and enabling optimization can lead to faster and more efficient code execution. In summary, algorithm complexity is influenced by various factors related to input, including process speed, disk speed, instruction set, and compilers optimizations. So understanding these features or factors allow programmers to analyze, optimize, and fine-tune algorithms for improved performance and scalability. By considering the impact of these input-related factors, developers can develop algorithms that help hardware capabilities effectively to improve and deliver optimal performance across different computing environments. So, what are asymptotic notations? The goal of computational complexity is to classify algorithms based on their performance. Time function, as we discussed in the earlier slide, that is represented as T of n. T of n time function is represented using big O notation to express runtime complexity of algorithms. So T of n is equal to O of n square, says that an algorithm has quadratic time complexity. In simple terms, the time complexity is double the size of input, or the execution time would be square of its input. Asymptotic notations are a mathematical way of representing algorithms' time complexity. Performance of an algorithm changes with change in input size. An algorithm can be analyzed in terms of time and space using asymptotic notations. Big O notation is one of the fundamental tools to analyze the cost of an algorithm. Big O notation describes complexity of an algorithm using algebraic terms. To understand big O notation, let us have an example. O of n squared referred to as big O squared, or it is read as big O squared. Big O notation is represented as a function such as f of n, where n is the input size. G of n is the complexity of an algorithm. Big O notation is used to determine the upper bound of an algorithm. F of n can be represented in terms of g of n as f of n is equal to big O of g of n. G of n should be less than or equal to c into g of n. That is, f of n less than or equal to c into g of n, where c is the constant and n is the input size. C, which is a constant term, should be greater than 0, and the input size should be greater than 0. Thereby, n should be greater than or equal to k, and k should be greater than or equal to 0. Now here, the O(n) square represents that uh, the time taken is squared of the input size. So as told earlier, f of n in big O notation, f of n is less than or equal to c into g of n, where c is a constant. Thereby, as told earlier, c should be greater than or equal to 0. Thereby, input size n should be greater than or equal to k, and k should be greater than or equal to 0, which means k can have only positive values. Big O notation is used to find the upper bound from the given equation here. The upper bound is n2. Therefore, f of n is less than or equal to constant c into g of n square. So 2n square plus n less than or equal to c into gn square. If c is equal to 2, then it becomes 2n square plus n, which is less than or equal to 2 into n square. If c is equal to 3, then 2n square plus n, where in the place of constant c we substitute 3, so it is 3 into n square. Similar to big O notation, big omega is also used for performance analysis or complexity of algorithms. Sometimes we say that an algorithm takes at least a certain amount of time without specifying the upper bound. Big omega is used to specify asymptotic lower bounds. In simple terms, an algorithm takes at least a minimal time to execute, that is, at least lower bound. The minimal time is represented using big omega. This can be represented as f of n is equal to omega into g of n. That is f of n greater than or equal to c into g of n. In big O notation, c into g of n greater than f of n, whereas in big omega notation, c into g of n is lesser than f of n. If f of n is equal to 2n square plus n, then the value of c, that is constant, should be lesser than 2, and the value of constant should be the greater lower bound. The values lesser than 2n square or n square, n, log n, etc. But the closest or the greatest lower bound is n square. F of n greater than or equal to c into gn square, substituting 2n square plus n greater than or equal to n square. If c is equal to 2, then 2n square plus n greater than or equal to 2 into n square. Therefore, 2n square plus n greater than or equal to 2n square. Thank you all of you for your patient listening.